All right. Hope everybody can hear me. Hello, everyone. Good morning or good afternoon. We have a very interesting discussion ahead of us. Let's talk about search and more specifically about information retrieval and how it works in a particular use case that we released in eBay very recently, right? I'm Senthilkumar Gopal, and with me is Deepika Srinivasan, and we are here to present about scaling ML embedding models to serve a billion queries. All right, so let's take a look at a search query and how the data flows in a typical architecture, right? Sellers come on to eBay and they create the listings, and we have about 1.6 billion live listings at any given point of time. These listings are stored in a database where then they are parsed for intelligent information extraction, augmentation, metadata processing, and then we index all this information into Cassini, which is eBay's search engine. So now, when a buyer comes in and attempts to query for pillows, say, right, there are many processes that occur in parallel. The category of the query is identified, the query is augmented to find out for more possible expansions, and then it goes through Cassini and finds the most relevant information, right? Just a fun fact, just in eBay German market, a car part or an accessory is sold every second. So that gives you an idea about the scale and the performance needs that we are looking in such a flow. So, but there's a particular fallacy here, right? User is always expected to express their intent using a shared vocabulary, right? Let's say it's colors, sizes, and sometimes even inexpressible intent. For instance, if the user wants to say that I want to buy a more red colored or a darker red colored bumper, or I want to look at a more wider pattern. So, is there a way for us to provide users with an ability to browse or discover their items without telling them to provide all this intent in words, right? Just to illustrate an example, think about this user. They want to buy a particular pillow for their couch. They try with different queries. They try kilim pillow, orange kilim pillow, throw pillow, orange kilim throw pillows, but they get good results. They get items which look very similar to what they want, but not the actual one they are looking for, right? And this is not an eBay problem, specific problem. This is not a new problem as well. But this is a problem that you will find in any application where search is a core functionality, right? So how do we approach this? So before we go into the solution, let's step back a bit and try to do a thought experiment on how k-nearest neighbors work, right? Let's assume all the items in eBay can be illustrated or set up as a two-dimensional object, primarily based on its item price and, let's say, the number of words in a title. Right now, it will be a very large space, but still it's a two-dimensional space where we have all the items laid out based on its item price and the number of words in the title. Right, so two pillows with the exact price and the number of words will be very close to each other, whereas motors or motor parts will be further away from this. Now, by any means, if we are able to express the user's query by text or any other mechanism within the space, then the discovery or the browsing is simply using k-nearest neighbors, which is very close to the query that they have provided. Now, let's see how this will function, right? And I know this is where the technical details are going to get a bit hairy, but let's walk through this slowly. Let's say we have two words, the word sofa and a couch. And by some means, we have a multi-dimensional representation of what these words actually look like, right? And once we have these representations, then we can actually figure out how similar or dissimilar they are using simple cosine similarity, which ranges from 0 to 1. Yes, of course, in reality, this is not just words. We can use it for words, sentences, or even images. And a full-blown representation in production looks like this with 768 dimensions, right? So how do we formulate these representations, right? So there's a famous saying by J.R. Firth where he says, you should know a word by the company it keeps. And this saying is pretty much the fundamental based on almost the recent NLP revolution that you're seeing in the past, in the recent past. Now, and the fundamental idea is very simple. Words that are used very closely in the same context or sentence are closely together in a space, whereas words that are seldom used together in the same context are further apart, right? There are many algorithms starting from word to vector, today's newest GPT-3 on how to generate these representations. A simple way to understand all these large language models, such as GPT-3, which uses this 45 TB of text data of Wikipedia and a lot of books, is that they try to represent these word representations. They just try to represent these word representations on based on the context that they have learned from those textual libraries, right? They are primarily trained to optimize for detecting synonyms or completing partial sentences. GPT-3 is just the latest model. Any large language model which can provide a good approximation of that particular word in the larger context of the sentences that they have been trained for is what a large language model is. So just to see how a language model would look like, we take one of the most oldest ones, word to vector, and we just put all the learnings of words it has on a 2D plane, right? Now you can see words that represent numbers are grouped together. Words that represent books are grouped together in a different space. And words that represent software companies are in a different space. The similarity is pretty much defined by the relative distance between these words. And this is exactly what J.R. Firth had explained earlier, that it is every word is dependent on the company it keeps. Right? Now, even more intriguing is that these word representations not just have good relative distance, they also capture semantic meaning, which means the distance between the words clear, clearer, and clearest, or loud, louder, and loudest, or to the previous similar example, light red, dark red, or crimson red, those distinctions or semantic meaning are embedded in the relative distance that you see, right? Now, we know how word representations are generated. Let's see how image representations are usually generated, right? So we use something called convolutional neural networks. In simple terms, neural networks, the first few layers learn basic representations, features like edges, lines, whereas the last few layers learn complex features from these small features that it does learn, even encapsulating large complex features embedded within it. So we simply take these last few layers and generate an image embedding or an image representation. And now we have both a textual representation and an image representation. Now, let's see how we actually put these together, right? So an eBay item has multiple data points, right, to hone in on a good representation. Better the representation, better is the recall, because then we will have good quality and the space will be finely tuned for each item, right? So to get a very good representation, we definitely need to use both image and textual data. So the neural network that we have used is inspired by a paper called CLIP from OpenAI, which uses something called contrastive learning. So contrastive learning is simply that it takes the image and the text data, which represents the same item, and then contrastively learns that these two represent the same item, whereas other image and other text do not represent this item, and moves them away. So intuitively, this moves items which share very similar text and image data closer together and moves dissimilar items away in a relative space. Right? On the right side, you will see the simple neural network model, or the model that we had used to train what we are going to see further. So we have dual inputs where we take in text input, and then we take image input, we encode, we transform, and then encode them or generate these representations. And then we feed them into a neural densely connected layer, which learns these true representation of an item based on both the text input and the image input. Because this works with two different modalities of text and image, this is called a multi-modal embedding, and this creates a really good representation of what an item actually means. Right? Now, you might ask me what goes into these image and text encoders. So we use BERT, which is a well-known language model for text encoding, and we use ResNet 50 to create these image embeddings, which are contrastively then learned to generate the final item embedding, and that's a good representation of how a final embedding looks like. So it is 768 dimensions in size, and it has encapsulated both the item and an image data in its representation. BERT is a large language model which has learned from a big corpus of Wikipedia and book corpus. ResNet 50 is trained on ImageNet data, which consists of millions of images. These are pre-trained models, and actually anybody can use it. They can simply download it. They can simply download it from Hugging Faces, and they can fine-tune it based on their own vocabulary for text or their own images, and then get even more fine-grained representations for their own workload. Now, we have answered one question, which is how do we generate these representations? The next question is how do we map them, or do we search them using cosine similarity? Now, all problems start with scale. This is a very common saying in large systems. If you recall our 2D representation, if we have all the items represented using just its price and title, the life would be so much simpler, because k nearest neighbors is a O of n problem, and we can still manage searching through this space. But with 768 dimensions, this becomes really, really expensive. And this is where approximation comes to our rescue. ANN, or approximate nearest neighbors, provides us a good approximation with a really good response time with a minimal loss of accuracy, which for search use cases is acceptable. There are many, many libraries and algorithms, as I've listed here, which support ANN. But we decided to go forth with IVF, or inverted file index, and product quantization for reducing the storage and the space that we need for storage, and also for faster retrieval. IVF uses something called clustering, and in simple terms, it breaks the whole search space of these 768 dimensions into smaller clusters, or more specifically called Voronoi cells. So once it has learned the data to break these clusters, when we search through this index, we don't search through the entire space, rather we search for neighbors only in part of the space thanks to this cluster and index, right? I know it has lots of information, and it's a whirlwind tour of what are the embeddings mean, how do we search them together. So let's all put all of this information and build our final pipeline, right? So we have this model training phase. In step one, we take the item that have been sold in the recent past, right? We take its item textual information and image information, encode them using BERT and ResNet 50, and we use contrastive learning, feed that into a densely connected layer so that we learn the multimodal embedding, right? In step two, we take this same item inventory, but then we take only its images, feed it through the multimodal embedding, and then use that embedding to learn an ANN index. And you might ask me, Senthil, why are you just using only images? You have both images and text, and I'll answer that in a quick moment. The step three is, once we have these image embeddings, we feed them into the ANN index for IVF, and learn and create this index so that it learns how to represent the clusters information, generate the code books for product quantization, and then we have our models trained. In step four, now we take the actual live inventory that we have on site, we take its images only, go through the embedding, the dense layer, generate the embedding, feed it into the clusters, and then we get the final PQ embedding. So one of the reasons why we do images only in this inference for ANN. We also do only images when we do the ANN index training. And I will, as I said, I'll answer that in a quick moment. Once we have this final PQ embedding, we then index it into Cassini so that when the visual cue comes in, we can do an IVF search using that embeddings for its nearest neighbors. Now, we have two questions, like how does this visual cue actually work? So that we give the users the ability to browse or discover through the space. And why are we doing only the images? The answer to this question is pretty much the same. If you recall our original example, the user is looking for a particular pillow, and they are not sure about what is the descriptive text they need to search for to get that particular item. So instead, this time they select an item which they feel is the most closest to what they want. And this forms the visual cue. So since it's a visual cue, we use the image of the item or the visual cue provided. We take that image and then we find its PQ embedding, and then we search through the ANN space for its nearest neighbors. Since the cue is in the form of an image, the ANN space is trained only with images, and that so that we can perform a true comparison, right? So it's a lot of information on how this model is trained, how do we generate these embeddings, how do we create this ANN space to perform the search. But this is not accomplished without a lot of operations and engineering which goes underneath. And I would request my colleague Deepika to give us a peek under this hood. On to you, Deepika.
Thank you, Senthil, for walking us through the details of the model that powers visual search for eBay items based on the similarity of their images. We have a question in the chat. Maybe we can take it now, or if you can address it on the chat itself, that'll be great too.
Sure. Do you concat, let's do it quickly. Hey, Gopal, thanks for the question. The question was, do you concat the text embedding with the image embedding for multimodal approach? We use the text embedding and the image embedding only for training the dense layer. But while inferencing, we use only the image embedding, as I told you before, because our use case for inferencing is for visual cues, and we needed only the image embedding to search through. So the ANN space has only image embeddings. But the multimodal embedding is trained to have a true representation. So think of this of kind of distillation of some sort. So we take the BERT embedding and we take the image embedding, and then we train another network which has a truer representation. So the final embedding that comes out represents the item. It's not a concatenation of just the image and the text. Hope that answers your question.
Cool. Thank you, Senthil. And Yusa, yes, the slides are going to be posted, and please keep the questions coming. We'll monitor the chat. And let's continue with the presentation now. All right. Okay. So Senthil walked us through the details of the model. So how do we productionize this ML pipeline? Are you able to see my slides? Do you see the data engineering slides, Senthil? Cool. Thank you. Okay. So let's see the architecture now. Okay, the overall design can be broken down into three components. The first is the data ingestion on the left, the second, model training, inference, and indexing, and third, the user experience. So starting from data ingestion on the left, sellers list their items on eBay. Item data and item images are stored in two different tables for efficiency of storage as well as retrieval. Now, the training data set includes all the recently sold items, and it is trained using the ResNet 50 image encoder and the BERT text encoder to create the embedding model that Senthil just explained. We can generate multiple models that are tailored to different categories in the eBay taxonomy. For example, we can have a model for furniture and another for electronics. So the training phase generates the model and the codebooks. So what is a codebook? A codebook contains the mapping of a centroid index to the corresponding centroid vector for the ANN clusters, and these codebooks are later used by the search engine to find relevant items at query time. So this completes model training. Next, coming to model inference. The model created is used to generate embeddings for the active items in the eBay inventory. These embeddings are then published to a Kafka queue and indexed in eBay's search engine that's called Cassini. Now moving to the user experience on the right, when a buyer using the eBay app on his phone comes across an interesting item like the throw pillow that Senthil just showed us and looks for similar items, the search service queries the search engine with the item image. The search engine generates the embedding for the query image and it computes the centroid that is nearest to it, and then retrieves a ranked list of items that are closest to that centroid and hence similar to the query item. And that's how a user is able to find a similar yet diverse set of results, that's pillows in this case, in the search results. So let's dive deeper into each of these components now. So coming to data ingestion, the item downloader is implemented as a Spark job and it reads item data from eBay's data warehouse that is hosted on HDFS, the Hadoop file system. The downloader filters active items from the inventory and it selects the relevant fields that are required for visual search. And this resulting data set is stored on HDFS as Parquet files. Similarly, the image downloader is also a Spark job that fetches images for active items by calling the eBay image service and stores these images as binaries along with their MD5 checksums. The checksums allow the downstream components to verify the integrity of the images and also avoids redundant downloads in subsequent runs. Now, Apache Spark was our preferred choice for implementing both the item and the image downloader because it's well suited for high-speed processing and transformation on distributed data sets, and it scales really well for our use case. Okay, so this is a simplified version of the image downloader code written in Spark. Now, this seems very simple, right? While it might seem so, there are several challenges running these jobs in a production environment that is shared with other systems. First, our image downloader was taking several hours to complete. And to speed up the job, we used additional compute and resources, but there's always a limit on resource allocation for every job to ensure that other jobs that are sharing the same queue don't starve. So to optimize resource utilization, it's useful to identify the non-peak times when the cluster has a lighter load and allows for more resources. Now coming to storage. As the size of image binaries for 1.6 billion items can run into terabytes depending on the number of images per item and the item resolution, it's important to optimize the download logic to avoid redundant downloads, also apply data compression, and implement effective purge policies to clean up any unused data and images periodically. Next, download errors are inevitable and they can be caused by multiple factors like intermittent network errors, missing files, file corruption, etc. And they can be mitigated using checkpoints, retries, and monitoring. And lastly, it's critical to avoid overloading the upstream service, the image service in our case, and risking its availability. The upstream service can throttle requests or even block callers suspecting a DDoS attack. We initially added more executors to our Spark jobs to speed up the downloads, but we started seeing a lot of errors as the image service had started throttling our requests. So it's important to communicate with the service providers and decide on the SLAs, allowed quota per tenant, and the rate limiting policies. Okay, so how is this data, image data, used further? So the images downloaded by the Spark job are stored as Parquet files on HDFS. Image binaries in these files are streamed using an in-house Python-based streaming utility, read as raw pixels, cropped and normalized to a tensor representation by a PyTorch application with multiple workers. The pre-trained image model reads this tensor as an input and it returns an embedding per image. Image processing and this embedding generation tasks run on PyKrylov, which is a Python-based interface to eBay's GPU-based AI platform that is extensively used for running ML workflows. The ANN index is created using the embeddings along with other item-related data fields and then serialized and published to a Kafka queue. Both the embeddings and the index are saved as Parquets for efficient compression and encoding. So here, there's a simplified version of the model inferencing code. The data flow that you see here refers to the in-house Python-based streaming utility that's similar to Hadoop streaming. It streams the binaries from image parquets. As each image is streamed, it's processed and passed through the model to generate the embedding. So next, how are these embeddings made available for search? So that brings us to Cassini indexing. The data acquisition pipeline that you see here is a lightweight event-driven system based on Kafka. It is used to annotate items with data points from various eBay systems. These data points include item attributes, translations, spam detection indicators, and so forth, and they enhance search relevance and ranking. The acquisition pipeline typically handles millions of new item events and a few 100 million item update events every day. For visual search, the image embedding vectors generated by model inferencing are published to the data acquisition pipeline as blobs for efficient serialization and storage. Now, the pipeline updates items in this search data store that uses HBase, which is a massively scalable distributed columnar storage, and it's a good fit for storing our item-related data. The pipeline ensures that the item updates are applied in the correct order in HBase, even if they arrive out of order from the upstream systems. Now, the next component, that's the item indexer, is implemented using Scala and Spark, and it reads these item records from HBase, denormalizes, applies required business transformations, and it generates a compressed and distributed index that's shipped to our Cassini query serving grid. Cassini is eBay's distributed search engine running on cloud that serves up to 1 million queries per second or about 100 billion queries a day. Okay, so now that we have gone over the architecture, how do we automate this workflow? So we use Airflow for our orchestration. Now the workflow is a DAG, that's a directed acyclic graph, with a sequence of tasks, with each component representing a task. We like the flexibility that Airflow provides for orchestration. Some tasks use Spark versions 2 and 3, some are Python-based ML tasks, and some are just bash commands and so forth. So given this workflow, we support multiple processing modes. So first is the bulk mode that generates embeddings for the entire inventory when a new model is onboarded. And it can also be used for ad hoc runs to regenerate the embeddings when there are any issues like, say, data corruption. Now, next is the delta mode that runs daily and processes items that are new or updated since the last run. Both the bulk and delta modes are offline. And finally, there's an online near real-time mode that processes items as and when they are updated. Now, how do we support multiple modes using the same DAG? So for this, both the bulk and delta modes are supported by parameterizing the same Airflow DAG, like you can see here. So depending on whether it is bulk or delta, we process all items or just the delta of items that were listed since the last run. Okay, now let's briefly touch upon the challenges that we faced using Airflow, and we'll briefly discuss how we overcame them. So the first challenge was orchestrating tasks using Spark versions 2 and 3. We use a lower version of Spark in one of the jobs as the Hive table that it queries is on a lower version. Now, as there can be a mismatch in parameters for Spark 2 and 3 jobs, we define task level configs instead of DAG level configs to avoid any conflicts. Now, second, for our ML embedding generation and inferencing tasks, we initially deployed Docker images with latest tags. With time, the latest tags started pointing to different versions of libraries, and this would cause compilation issues. So as an easy workaround, we moved to Python virtual environment packages that bundles the ML scripts and their dependencies together. Now, there can be issues around data movement when data is on different availability zones, platforms, etc. Now, there's always network flakiness, service and storage disruption that's caused by factors beyond our control, like, say, wildfires and so on. So retries with exponential backoffs, monitoring, and alerting can help mitigate such failures. All right. So now that we have a model and a workflow serving production, let's say we want to try a different model that uses a different algorithm for embedding generation and compare this new model with the one serving production. So this was the design that we had for a single model. And now how do we extend it to be used for multiple models? So here to enable A/B testing, we extend the same design so that the same item and image data can be used to train two different models. And these embeddings are also generated using both the models A and B, as you can see here. Now, when the user queries for an item, there is a new component that's in orange. That's the eBay experimentation service that decides whether the user falls in group A or group B, depending on a number of factors. And Cassini consequently uses the embedding for model A or B to retrieve the relevant items. So thanks to Airflow, we achieved this concurrent data publish for A/B testing by creating two parallel sub-workflows, both of which share the same image and item data. The embeddings and index for both the models A and B are pushed to the search engine. These are the graph and the tree views for the Airflow tags taken from the Airflow UI. Now, as you can see from the tree view, we use several operators provided by Airflow. And in addition, we have also implemented our own custom operators for eBay technologies, like the Pi-Krylov operator that you see here. Okay, now that we have covered so many different technologies and systems, Here's our tech stack captured all in one slide. We use several open source technologies along with eBay specific software. Some eBay components are built on top of these open source technologies with additional features for logging, monitoring, etc. Okay, so far we have a model running in production. Now, how do we ensure that this model performs well and remains relevant over time? That brings us to the last slide. It's important to monitor the model for drift, which can be caused by data drift and concept drift. Now, data drift happens when the training data gets outdated and has a different probability distribution than the new data. Now, this is especially true with seasonal data. So let's say that the model was trained around Halloween. Now, recommendations around Christmas may not be as relevant as the data distribution has changed. Concept drift can be addressed by tuning the hyperparameters for the model. Next, coming to aging of the models. Now, this can result in suboptimal predictions. So it's important to evaluate newer models that perform better and can replace the current model. For example, we currently use ResNet 50 for image encoding. Maybe they can be replaced with vision transformers or VIT in future, depending on the performance of the new model. Now, some metrics that can be used to monitor the model performance and embeddings are accuracy, precision, recall, F1 score, mean squared error, etc. Now, monitoring the embedding performance can help us identify parameters that need to be fine-tuned over time. Whenever these metrics drift from the ideal stats beyond a certain threshold, it is time to retrain the model or revisit the model parameters to improve its performance. Coming to system monitoring, data integrity checks are required to make sure that items and images are not missing in the training and inference data sets. We, for example, use MD5 checksums to make sure that the image binaries are not corrupt. So scaling ML pipelines requires every component to be fault tolerant and resilient. This is achieved by adding checkpoints, retries, monitoring, and alerting. Now, system health checks involves monitoring the service response time, CPU, memory, and disk usage to make sure that the engineering components in the ML pipeline have optimal performance. So in closing, vector embeddings play a crucial role in semantic search. They can offer a superior search experience in multiple domains, including e-commerce. Now, while designing and developing ML pipelines for embedding-based search, it's important to make sure that every component is fault-tolerant and resilient. And it's also critical to revisit the model performance from time to time to make sure that it is performing well. And that brings us to the end of the presentation. And we are happy to take any questions now.
Deepika, there are tons of questions, and thanks to everybody for all the questions. Hope I had answered some of them. Yes, but please do keep the questions coming.
Thank you, guys. This is very encouraging. Wow, it's a busy chat here.
Yes, I think Bhakti had a question, how often we train the embeddings itself. So the model training is so as you saw, there are kind of two pieces, right? One is how we generate the item embeddings that we have the final multimodal embedding for. So that is we don't do it often right now. If I remember, I think it's monthly, right? Monthly or maybe on demand. So that's where we look for model drift. Since we use a large amount of data to train it, we don't expect it to drift very quickly. The idea is we try to keep the model parameters within line in check. And if we do see some deviations start to happen, then we get a bunch of fresh data and try to train it. And since we have released this right now for home and garden in a particular category, that also helps us keep the drift to within particular parameters. Hope that answers your question, Bhakti. And Yusu had a question for the text model part. What features are embedded? Yes, it's currently it's title, and I think I answered that earlier as well. Currently it's title, but we are experimenting with title aspects, descriptions as well to see which works best. So a lot of hyperparameter tuning and determination is experimentation, and we try to align to see which works best. So even for and indexes or for which model parameters work, that's kind of the way we go. Okay, Richa had a question. What processes do you have for retraining? Is it automated? Deepika, you want to try at answering that one?
Sure, yeah. Actually, it is fully automated. The process that we use for the bulk mode, the airflow DAGs, can also be used for retraining the model itself. Of course, the parameters would have to be tuned, and those would have to be manually changed and updated.
Thank you. How do we? Okay. Bhakti had a question. How do we detect drift in embeddings, and how do we address drift? Do you want to take a
Okay.
stab?
So,
Yeah.
yes. So we continually monitor the metrics that I just went over, the accuracy, precision, etc. And we can have thresholds that are acceptable. And whenever they deviate more than this certain threshold, we know that it is time to retrain the model and regenerate the embeddings.
Okay. Nicholas had a question. Sorry, I skipped the question, Nicholas. Could you give more details on how you train the model with the two modalities and different embedding losses? Yes. So, without wasting a lot of time, I just want to make sure. We'll keep it simpler. So we have the image embedding from ResNet. So it's just the last layer, and we have the classification token embedding from BERT. Then we use contrastive learning, which is essentially triplet loss. We take a positive sample. So the positive sample is what you would see in the diagonal, which is whether the text and the image points to the same item. So that forms the positive samples. And the other samples that you see, which is non-diagonal, are all contrastively negative samples. So we take a batch of 64. The batch runs in terms of loss calculation is, okay, this is the diagonals are the positive ones and the off diagonals are the negative ones, and the loss gets back propagated. A simple way, actually the better way for you to look at it is look at the original clip paper from OpenAI. And I think there's also a PyTorch implementation of it, which is like the basis on which we did this one.
Okay. Mukesh, thanks for pointing it out. We were waiting for this presentation to end. We'll upload the slides right after. And we have another question on index sharding.
Yeah.
Is the structure capable of scale out? Yes, it is. So sharding is done depending on the number of items we have, the memory, CPU, etc. on each column or node. So the grid itself is composed of several rows and columns, and we do LNP tests to find out the optimal size and number of shards to go with. We hope that answers your question.
And just to point out, Mukesh, I think the slides should be available now. Sorry about that. Thank you.
Great.
Thanks for
Thank
pointing
you.
it out. Chris had a question around, do you use any offline metrics for evaluation of the performance? Yes, for the multimodal embedding, we do have a paper coming out soon. So I think that will formulate a more clearer answer, but we do use MAP, mean accuracy, and also NDGC within a leaf category to see how much of the embeddings actually help us with recall. And that's just a couple of metrics. We also have more detailed metrics. Sorry, I cannot recall it right off the top of my head, but if you can look out for the paper, and maybe we also will follow up a blog post with more details around the technicals of it, that should help. Thanks, Mukesh. All right. If we did miss any question, please do repost it. And I think we have maybe another minute or so we can go and we can answer it. Yeah, thank you, folks. Thanks for the kind words. Really appreciate it. Thank you, everyone. And again, we are both on Twitter and on LinkedIn. And of course, feel free to hit us up and we will try to answer as well. Thank you, everybody. Have a good next day. Enjoy.
Thank you, everyone.